Okay, so good morning, everyone. My name is Pratika Dayal, and yes, I'm here, a local person from the Kapsain Institute. And today, what I would like to do is take you a little bit back in time and talk to you about the information that we have from the cosmic dark ages. So I thought I would just start by putting this issue of the cosmic dark ages in perspective. And so here, what I'm showing you is a picture of our cosmic history, which we have very, very painstakingly built up over decades of observations. And what we are now understanding is that our universe started roughly 13.5 billion years ago in some sort of an explosion called the Big Bang, after which the universe was basically just expanding, and as it was expanding, it was cooling. And finally, about 400,000 years after the Big Bang, for the first time, the universe was able to cool enough that electrons and protons finally started recombining to form what we call neutral hydrogen and helium. And this, immediately after this era, which leads to the rise of what we call the cosmic microwave background, which I think will be discussed tomorrow in more detail, this is followed by what is known as the cosmic dark ages. And this era, which lasts a few 100 million years, actually, for the first billion years, is called the cosmic dark ages because at this time, all that is happening is that a kind of matter, which we call dark matter because we don't really know what it is, and this is the dominant kind of dark matter in the universe, is trying to collapse to form some sort of halos, but no ordinary matter, like anything which we know about, has started to cool inside these halos to form stars. So there is no light in the universe. The universe is actually completely dark, hence the name, the cosmic dark ages. So these cosmic dark ages last a few 100 million years, and they end with the formation of the first stars inside galaxies. Now, what these first stars start to do is they are surrounded by hydrogen and helium, and these first stars produce the first photons or the first light, which can again break up this hydrogen into its constituent electrons and protons, starting what we call the epoch of cosmic re-ionization. And what I've tried to show here is some sort of a very generic image about what reionization looks like. So in the beginning, you have small galaxies forming stars, which start to ionize small regions around themselves. As time goes by, these regions grow larger and larger in size until these ionized regions will cover all of the available volume of the universe. This, we think, happens somewhere in the first billion years of our cosmic history. And what is really critical is that once the universe is reionized in the first billion years, it then remains reionized for the next 12.5 billion years. So we live in a universe which is completely reionized. So now that you have, and I should have said we are here roughly 13.5 billion years after the Big Bang. So now that you have an idea of our cosmic history, let me start with the actual talk, where I would like to try and answer 3 questions. Why is it even important to understand these first galaxies? They formed roughly 13 billion years ago, so why should we actually care anymore? What is the key physics which is driving these early galaxies? What can we actually learn from all of this information that we have now from the first billion years of the universe? And how can we actually say something about the reionization state of the universe using the data that we have now? So, of course, everything that I'm going to show you today has been done in collaboration with a number of amazing co-authors who are listed here. I'm going to show you a lot of data from things like the Hubble Space Telescope, the Atacama Large Millimeter Array. And all this is as we look towards getting more and more information from this era of the cosmic dawn and the cosmic dark ages from the Square Kilometre Array and Euclid. And I think Henk is going to talk more about Euclid tomorrow. So let me start with what exactly is a galaxy. A galaxy is just a conglomeration of stars, gas, dust, maybe even black holes. And here I'm showing you the image of a galaxy, which is a spiral galaxy because it has these spiral arms. Our own galaxy, the Milky Way, is also a spiral galaxy. And so here you can beautifully see a number of stars. You can see they are surrounded by a lot of gas and dust. So this is basically what we are going to call a galaxy. So the question is, what exactly do the first galaxies do? So here I'm showing you a simulation that we've run to understand the formation of galaxies over 13 billion years of cosmic time. And what you can see is that the initial universe is actually a very is very well ordered. It is very homogeneous. It looks very, very isotropic no matter where you look. But as time goes by, tiny fluctuations which are left over from the early universe will grow to form galaxies. And here, each of these dots that you see is actually a galaxy. And as Peter was telling us, things attract. So here, what you find is, wherever you have an overdensity of galaxies, more and more galaxies stick together to form larger and larger systems. And as you zoom through the simulation box, you can see these beautiful structures, which are actually much more clear on my laptop, of cosmic filaments, which are regions which have a lot of galaxies embedded inside them. Galaxies form at the intersections of these sorts of cosmic filaments. And here you have regions which are called voids, which are underdense regions in the universe, where we don't have any kind of galaxies forming. And so this is actually the pattern of the large-scale structure of the universe, which persists once galaxies actually start forming. So this is another example of patterns in the universe which have actually persisted throughout cosmic time. And here we are talking about 13 billion years of cosmic time. And I think everybody kind of saw, so one of these tiny galaxies which we see can actually be galaxies like our very own Milky Way. So these first galaxies are actually progenitors of systems like our very own Milky Way. So our cosmic origins actually lie in the formation of the first galaxies which were forming in the first billion years. These first galaxies are also critical because before these first galaxies started forming, the only elements we had in the universe were actually hydrogen and helium. Once the first stars start forming, some of them will actually start exploding in massive explosions called supernovae, and these are actually the birthplaces of the first metals in the universe. And metals can be anything like lithium, beryllium, boron, iron, magnesium. All of these elements that we are so used to seeing actually had their origins in the first supernovae, in the first star formation, in the first galaxies. So these galaxies were actually critical to form stars like our very own sun, which is a very, very metal-rich star, as compared to something which formed out of no metals whatsoever. And then these first galaxies were also the key sources of all reionization photons. So as we discussed, when the universe started, it was basically full of hydrogen and helium. Let me forget even about helium. Let's just say the universe was full of hydrogen. So imagine this universe to be full of hydrogen, and now the color is black, which is let's say it represents hydrogen. Once the first stars start forming inside the first galaxies, they will start ionizing or breaking up the hydrogen around themselves into electrons and protons. And I apologize, but you can't see the colors really well, and this is actually shown by a kind of blue color. As time goes by, these ionized regions start growing, they start overlapping, they start merging, giving rise to beautiful patterns, kind of like a Swiss cheese topology. So now you can start seeing these colors slightly more clearly. These ionized regions grow in time, they merge with each other, until at some point, all of the available volume of the universe will be reionized. And this is when we say that the epoch of reionization is complete. And I would just like to remind you, once this epoch has taken place in the first billion years, the universe has remained reionized for the next 12.5 billion years. So really, the first galaxies were critical not only in ushering in the era of all of structure formation and the era of the first metals, but also the era of cosmic reionization. And together, these have shaped the universe that we actually see around us. So I hope by this time I have convinced you that it is actually critical to look at the first galaxies which were forming in the universe. And we live in a golden era in our hunt for these first galaxies. So about even 7 or 8 years ago, we had one galaxy candidate which we thought formed in the first billion years. But then the wide field camera was installed on the Hubble Space Telescope, and since then this field has just exploded. As you can see, we have now more than 6,000 galaxies which formed in the first billion years. Redshift here is just an indicator of the age of the universe. So 5 is galaxies which formed in the first billion years, 10 is galaxies which were forming in the first 400 million years of the universe. And of course, this has been made possible by amazing surveys ranging from the ultra deep field, which is looking for the faintest galaxies in the universe, the Borg survey looking for the brightest galaxies in the universe, lensing surveys with the Clash and Hubble, a lot of different instruments which are giving us information at different wavelengths, and so on. And so what we can actually do is, using all of this data, we can actually start to say, well, what exactly are the key properties that we are looking at in the first billion years? So I don't want you to really remember anything. I'm just showing you this as an illustration of the amount of data that we have actually been able to build up over the first billion years. So because we have this amazing amount of data, we can finally start to do some sort of statistical analysis of what we can actually infer. So the first thing that you want to infer is, how many galaxies do you have in a given volume of space as a function of the luminosity, which is just the light. So how many galaxies do you have as a function of their light? What is the relation, for example, between the total mass that is locked up in stars in a given galaxy as a function of light? So these are two of the most critical quantities that we actually use to try and understand the formation of galaxies. Because we have this data, we can actually now start to ask, how exactly are galaxies building up? And so far, what we understand from the point of view of galaxy formation is that galaxies form in two main ways. The first is that they can just eat up the gas that sits around them in the generic universe, which is called the intergalactic medium between galaxies. And the second way in which galaxies can build up is what is known as mergers. And here is an example of a merger between two galaxies. So here you have two different galaxies which are now merging with each other. But mergers don't happen instantaneously. They happen over time scales of maybe, say, billions of years. So for example, our own galaxy is going to merge with our most nearby galaxy, which is called Andromeda, over the next billion years or so. As you saw, these two galaxies have passed through each other. They have lost some amount of energy, some amount of momentum. And so then they are going to now again go into their second interaction. And at the end of this, you will be left with a galaxy which has gas and stars and dust probably from both of these galaxies. So these are the two key ways in which galaxies can actually build up their gas mass. And what we can do now is, because we have all of this data, we can actually start putting this into perspective. So here again, I'm showing you the number of galaxies that we have in a given volume of space as a function of luminosity or light. These are faint galaxies. On this side are bright galaxies. All of these different lines show you the results that we have inferred at different cosmic epochs. So for example, the lowest line shows you the number of galaxies that we have per unit volume 100 million years after the Big Bang. This is something, the black line is the result for galaxies a billion years after the Big Bang. What we are beginning to see is that everything that we see converges towards the picture that we have, that galaxies assemble hierarchically. You have little galaxies forming in the early universe, which merge through time to form larger and larger systems. As a result of which, you have a very large number of low mass or faint galaxies. These have to merge to form larger systems, and so the number of larger systems that you see at any cosmic epoch is much lower than the number of smaller low luminosity systems. What we also see is that the total number of galaxies that you have continuously grows with time as more and more galaxies are forming and merging with each other. And most critically, in terms of galaxy formation, what we have been able to infer is that the large number of these very faint galaxies are actually driven mostly by gas accretion from the generic gas which surrounds galaxies. However, the formation of these most massive galaxies is actually dominated by mergers, which I showed you between different galaxies. However, what I have to say is that these galaxies are all forming against this patchy background of reionization. So a brief reminder, as galaxies form, they will start to carve out regions of ionized hydrogen around themselves. which will slowly grow and merge through time until all of the available volume of the universe will be actually reionized. The challenge is, how exactly do you shed any sort of light on this patchiness of reionization? And so basically this is what I work on, and this is to use a specific class of galaxies called Lyman alpha emitters to say something about this patchiness of reionization. So without going into any kind of detail, Lyman alpha emitters are just galaxies which have a Lyman alpha emission line, and this is the most common emission line that you can have from neutral hydrogen. So the idea behind this calculation is really simple. Let's say you have a small galaxy sitting here which produces Lyman alpha. Lyman alpha gets very easily scattered away by hydrogen. As Lyman alpha comes out of this galaxy, imagine that your universe is basically composed of neutral hydrogen. As Lyman alpha comes out, it finds neutral hydrogen, completely gets scattered away. So you would not see any of these little galaxies as Lyman alpha emitters. On the other hand, imagine that you have a large number of galaxies which sit together, and they can carve out a large ionized region around themselves. Let's say all of them produce this Lyman alpha emission line. As the Lyman alpha comes out, it doesn't find any neutral hydrogen, so it keeps coming towards us. We are the observers sitting here. And if this ionized region is large enough, some or all of this Lyman alpha can actually come out and will be seen by us. So galaxies which sit preferentially, which are clustered, which sit in ionized regions, can actually be visible as Lyman alpha emitters. On the other hand, isolated galaxies will not be visible as Lyman alpha emitters. And now let's link this to the second part of the puzzle which we had, which is, in the beginning, the universe will be completely neutral in terms of hydrogen. As time goes by, these ionized regions become larger and larger until all of the available volume will be completely full of ionized hydrogen. What this naturally means is that there must be a huge subpopulation of galaxies which are hidden in Lyman alpha in the initial stages of reionization, and they all become visible slowly as time goes by and reionization proceeds. And indeed, these are the kind of studies which we can now do with the Hubble Space Telescope. And here I'm showing you an example of two Lyman alpha emitting galaxies which have been found at a redshift of 7, which is roughly 700 million years after the Big Bang. So we can now look back in time, get information from the first 700 million years of the universe, and we can actually confirm the fact that these sorts of galaxies are really living in very, very dense regions in the early universe. And this is why they are actually visible in terms of Lyman alpha. So we can actually start saying something about the patchiness of reionization using galaxies which we can now detect with the Hubble Space Telescope in the first 700 million years of the universe. But this is only with regards to galaxies. What about the neutral hydrogen which sits in the universe? So neutral hydrogen has a very, very nice property that when the electron and proton are aligned with each other, it is in a high energy state. Everything in the universe tries to go towards a low energy state. So the spins of the electron and proton can actually flip, which is what is shown here. And when these spins flip, this gives energy or a wavelength which corresponds to basically 21 centimeters. This is exactly what things like the Square Kilometre Array, which is an international consortium, are trying to look for. So what the Square Kilometre Array does is, this is a huge amount of telescopes which are going to be put together to look for this 21 centimeter emission from the very early universe. So the idea is of what we are trying to do is the following. Imagine this is your universe. You have a lot of information, and all of these, the yellow color basically shows you neutral hydrogen. Green and red shows you hydrogen which has been ionized. In principle, what things like the Square Kilometre Array will do is that they will be able to image all of this neutral hydrogen, so they will be able to image the yellow color which you see here. On the other hand, we have a number of galaxy observatories which are probing the same cosmic epochs, which can actually tell you where galaxies sit inside these ionized and neutral regions. So for the first time, what we are going to do is to be able to build a complete picture where we not only have a picture of the hydrogen in the universe, but we can also relate it to what are the galaxies which are actually causing this process of reionization, and where are they inside the ionized or neutral regions that you see in the universe. So for the SKA, it can only see these yellow patches. The red and the green patches will actually look completely black. And on the other hand, in the galaxy part, you will start to see all the galaxies which are embedded inside. So this all seems relatively straightforward. So you can say, okay, so we do a lot of statistics, so we can start to do statistics which link actually these laminar flow emitters and the 21 centimeter emission. And what we can start to do is to try and build what are called correlation functions. And correlation functions just tell you what is the strength if you correlate one property with another. So for example, here we are correlating how much 21 centimeter emission do we have, so how much neutral hydrogen do we have, and how many laminar alpha emitters do we have as a function of radius. How are these two things distributed with respect to each other as a function of scale? So what we see is that when the universe is half neutral, these two quantities are severely anti-correlated. So 0 is here, so no correlation is here. When the universe is half neutral, half ionized, these two properties are severely anti-correlated. What this means is wherever you have neutral hydrogen, you don't see anything as a laminar flow emitter. As the universe becomes more and more ionized, more and more galaxies become visible as laminar flow emitters. So the strength of the laminar flow emitter part increases, but you have no 21 centimeter emission because your hydrogen is becoming more and more ionized. So the neutral hydrogen is basically disappearing. Once the universe becomes fully ionized, you have no neutral hydrogen. So this 21 centimeter emission part basically disappears, and all you are left with is your laminar flow emitters, which means that this correlation basically goes to 0. So this is just to give you a very broad idea of the kind of calculations which we are trying to do for to shed light on this topology of reionization. And what this basically, the bottom line is that doing these sorts of correlations between neutral hydrogen and galaxies, we can actually try and shed light on the neutrality of or the reionization history of the universe. So we should be able to distinguish between a universe which is, say, 10, 25 or 50% ionized. And I know this doesn't sound really impressive, but so far we are struggling with numbers which is between 0 and 100%. So in the future, we can really try and shed light on the history and the topology of reionization. So till now, everything has been really beautiful. We have these well-controlled error bars. Everything seems to be kind of making sense. The problem is the huge amount of information that we actually expect over the next couple of years when we try and do these kinds of calculations. And so this is why I called it an information deluge. So let's just focus on the Square Kilometre Array, which is going to look for neutral hydrogen in the early universe. Let's just ignore galaxies for now. So the SKA is an instrument. It's a collection of telescopes which is going to be built in Australia. The total collecting area is really huge compared to what we are generally used to in the field of astronomy. But what I would really like you to focus on is the amount of data that will be generated. We are expecting roughly 5 zettabytes of data per year. I didn't know what a zettabyte is, so I had to look it up. It is 10 to the 21 bytes of data. This is how much data we are going to be generating per year, solely for how much hydrogen do we have in the early universe as a function of time. And now the question is, how do we actually reduce this data to be able to actually infer anything, to be able to do science and come up with these sorts of correlation, to be able to come up with these sorts of pictures. So right now, really the bottleneck is really trying to understand the information which the universe is giving us over the first billion years regarding even just the amount of hydrogen that we have in the universe. And so I think I would just like to end here by giving you this picture which has emerged over the past roughly 10 years regarding some of the earliest galaxies in the universe. And what I have tried to show you is that we are in this golden age where we can actually now really start to shed light on the first galaxies which were forming. And these are crucial because they were the first building blocks of all the structure that we see. They were the seeds of all of the structure formation or the large-scale structure patterns that we see imprinted in the universe. They were the first sources of all metals. They were the first sources of all reionization photons. So far, thankfully, all the data that we have confirms our standard models of galaxy formation. Little galaxies will merge through time to form larger and larger galaxies. And now we can actually start to ask, are we looking at how are galaxies actually forming? Are they forming mostly through accretion of gas? Are they forming through mergers of gas? And so we can actually start to test all of these models all the way back into the first billion years. So now we can in principle build a consistent picture of galaxy formation over 12.5 billion years of cosmic time. And finally, what I try to show you is that this is just one part of the picture, which is galaxies. We also have another part of the picture, which is provided by hydrogen, which is spread throughout the universe. And this will be probed actually by the Square Kilometre Array. And really, the bottleneck now is to really be able to somehow process all of this huge amount of information that we are getting from the early universe. And I would just like to end here. Thank you.
Okay, thank you, Pratika, for that very nice talk, and also to keep it scrupulously to time, which makes my life easy. Questions? Sorry. So, thank you for the talk. I was just wondering, these Lyman alpha that suddenly pops up when you have a certain concentration of those clusters coming together. Is there like a critical transition in that? Is like a smooth process that suddenly smoothly those Lyman alpha signals pop up, or is it like you don't see them for a time and suddenly they are there? How does it go? Is there a threshold that needs to be passed?
Oh, it's a very, very nice question. I wish I could answer it. So I think I've spent the past 10 years trying to understand this. And the problem is that it really depends on the distribution of galaxies, which you can somehow try and infer from this large-scale cosmic web. But it also depends on how large is this ionized region around the galaxies. I didn't get into the details of this, but it also depends on velocity fields. So is this Lyman alpha actually pushed away by the galaxy, or is it being pulled into the galaxy? It depends on how much dust each of these galaxies have. So it's really a very, very complicated process. So what we find is that it's very patchy. You have regions where Lyman alpha just pops up. So for example, here, we actually had Lyman alpha popping up from this galaxy in the beginning. And then we were looking more and more with this Hubble Space Telescope. And then suddenly we saw another one. And so the question was, wait, why are they so close together? And so we looked in more detail, and we found that this is actually a clustered region. So each of these dots that you see is actually a galaxy. And so I think this is one of the key problems. There is no specific threshold of the size of the ionized region, but it really depends on how much Lyman alpha can these galaxies actually produce. Is it pushed out, pushed in? How large is this neutral region? So yeah, it's a really complicated process.
So if you allow me a related question, so you expect that this goes on, this reionization goes on forever? I mean, at some point you're losing energy or whatever, you get less density or something is happening. So you see this build-up of reionization over the years, and then it stays like that.
Oh yeah, then yes.
At some point it would disappear or so.
Oh yeah, but okay, so basically what happens is that once reionization finishes, so all of the hydrogen in the universe gets ionized. And after that, in principle, we are always building more and more galaxies, more and more stars. And so then, once reionization is finished, we think we have enough photons to keep it reionized. And this is why once you get to reionization is over, it just stays like that for the next 12.5 billion years. Yeah.
Oh my God, I'm not on that side. I'll come do that in parts, I think. Oh. There was a hand up towards the back. Sorry, it's hard to see.
So I have a comment and a question. The comment is the picture that you were referring to in terms of galaxy formation assumes that is in the cold dark matter scenario where you assume that first you form the galaxies and then you form the stars.
Sure.
But there are other pictures in which you can form the stars like in warm dark matter
Sure.
in the filament before you form the galaxy, and that triggers galaxy formation. and that can explain the supermassive black holes at earlier galaxies. And you wouldn't be able to, with this observation, to distinguish in between which is what.
Oh, no, actually you can. This is a really nice question. Sorry, I didn't talk about warm dark matter at all because it was just, yeah, too much. So in principle, what actually happens is that, okay, let me just show you maybe this picture. So indeed, this is galaxy formation in the standard cold dark matter paradigm. And we have also done exactly these same calculations in warm dark matter. What happens in warm dark matter is that, so cold dark matter, just to clarify, is this kind of dark matter which is very cold in the sense it doesn't have a very high velocity, so it's very sluggish. Wherever you put it, it will try to find more cold dark matter and it will try to clump with it to find a galaxy, to form a galaxy. Warm dark matter is something which has a higher velocity. So warm dark matter particles kind of, they don't sit next to each other, but they will fly around. So they find it hard to form very, very small galaxies. So what will happen in warm dark matter is that, let's say, these low mass galaxies will actually not form. So all of structure formation gets shifted to later times, which means that in principle, reionization gets shifted to later times.
Yeah, I disagree with that because I've done for a very long time warm dark matter simulations, and I know
Yeah.
the present resolution that people do warm dark matter simulations,
Yeah.
that's exactly what you get.
Yeah.
However, I would like to remind you, and we had this discussion at the Marcel Grossman meeting a few years ago with Tom Tunes.
Okay.
There was that very high resolution simulation that they did in 2007,
Yeah.
where they actually showed that you can form stars in filaments before you form the halo.
Yeah.
That can actually trigger the formation of galaxies. So
No, it's the other way. It's not completely correct. Okay, so you can form stars, well, maybe inside filaments, which can provide some contribution to reionization photons. The problem is that it is not completely, it was fine when they did it, which is a couple of years ago, but now if you compare it to the data which we already have, it doesn't work. So you don't get the right number densities of galaxies. And also, well, maybe can we discuss this later? Because, you know, I think the problem is really how you do galaxy formation. So for example, if you run simulations purely with dark matter, and then you stick on galaxy properties, they look very, very different to if you actually simultaneously model dark matter and baryons. And so this is the point which I was trying to make in a rough way. Yeah.
I don't trust any warm dark matter simulations.
Cool,
because
okay.
they have high resolution. So, but anyway, my question actually was
Okay.
not the comment. My question actually was, you said that the galaxies that form through mergers are much brighter, and the other ones that are faint are forming through accretion.
Well, okay, so yeah.
That's kind of the trend. Yet we do see pure disk galaxies
Yeah.
that are formed that are quite bright in the universe.
Sure.
And we know that in EM simulations, plus baryon, minus baryons, you
Yeah.
don't preserve the pure disk precisely because you have a lot of mergers that
Sure.
perturb the pure disk.
Oh, sure. Yeah. Oh, sorry. So let me just clarify. So everything I was talking about is in the first billion years, right? So in the first billion years, actually, we don't have disk galaxies. Everything is still merging. So you don't have enough dynamical timescale to actually form a disk.
So your answer would be that the disk is actually a dynamical effect that happens
Yes.
later on due to baryonic effects.
Yes,
inside
of
the-
course. Yes. So also I should clarify what I wanted to talk about was actually the gastrophysics of early galaxies. Sorry, I was not talking in detail. It was a very general talk. So yeah, the way galaxies gain gas is actually different. So it is smooth accretion when you talk about low mass galaxies, and the the way in which galaxies gain gas is actually dominated by mergers when you look at more higher masses. So it was mainly about the way in which galaxies are gaining gas rather than in which they are gaining stars or building up their stellar mass.